So we experimented with other camera sensors with embedded processing and found that the tiny infrared camera that is also used in the Wii remote control that tracks infrared blobs over time and sends it via Bluetooth to another computing device. So this already shows the potential of this technology to be more in the shape of a wristwatch in future. So our latest system is called FloodLight, which was developed for 3D silhouette sensing for high precision input on and above physical surfaces. So as you can see it on the slides, there are already many ways to interact more naturally on a PC, with touch on surfaces, with a stylus for more precise input, with tracked tangible objects, and also since Kinect, Leap Motion, and similar sensors, also in 3D in midair. However, we need separate sensors for all these modalities, and if we want to combine them together, it's hard. They don't play well together, and all these sensors need to be calibrated to each other. So the question is it possible to combine all these modalities? So we could, for example, use a depth sensor like Kinect or similar sensors, but they don't offer the necessary precision as they were developed with tracking coarse body motions in mind. And a 3D motion controller like Leap Motion, they are quite precise, but they are only limited to tracking fingertips that are in midair. So motivated by this problem, we accepted the challenge and we developed FloodLight. So FloodLight is a single sensor for robust pressure-enabled touch, stylus, tangible objects, and midair interaction. And here we demonstrate the manipulation of virtual objects using on-surface and as well as midair gestures. And we can also use custom physical widgets like this color wheel to control parts of the user interface. And we also allow for more precise input with pen or any other pen-shaped objects. So by letting users seamlessly switch between pen, touch, and freehand 3D interactions, as well as the use of physical interaction widgets, FloodLight offers a really extremely rich interactions in a variety of styles within a single package. So here, a little trackpad is used to control the camera of the scene. And the hardware setup itself is fairly simple. It's cheap and it's fairly easy to reproduce. So here we use a pair of infrared cameras, diffuse infrared LEDs, and off-the-shelf retroreflective material, a material that can be found on sportswear or like on bicycles. And this material just aids the segmentation of objects by enhancing the contrast in the camera images for objects that are positioned between the camera and the surface. So the property of this material is that light coming from other sources, they will simply bounce back, and only light shot from the direction of the camera will bounce back to the camera. So, so with this simple trick with optics, we can keep all the smarts in the camera and leave the whole interaction and touch area free from any electronics. So that reflective material is also tracked, and we can sense 3D contours of the hand above the surface. And we can also extract the fingertips, as well as their pointing directions. And we can also extend this mechanism to even detect pen and other pen-shaped objects. And when tracking hands and fingers, FloodLight also offers touch detection with sub-millimeter accuracy, and as well as information about the distance of the fingers relative to the surface it's interacting with. So it gives us hover state. And we can also reconstruct the full depth map from the 3D contours of the tracked objects, for example, for more sophisticated applications. So this is the image processing pipeline in motion. So we see two rectified images from the stereo cameras. This is all the input signal we get from the FloodLight system. And the objects placed on top of the retroreflector, they can easily segment it by masking out the convex hull of the reflective material. And once the objects are segmented from the background, our novel stereo algorithm efficiently recovers the depth from these contours, and which we visualize here in false color mapping. And we can also interpolate the depth between the contour points. So the 3D motion tracking is very robust and fast, only because our images are virtually already segmented and binarized. We have a clear segmentation. And in our processing pipeline, we simply trace the contour of the objects and don't use the whole image. So we don't use all the megapixels of the camera images, but only use the contour points to extract the depth. And this simply removes the need to do a search over the whole image and make this approach unique and very fast. And the contour path is also used for some post-processing steps, for example, smoothing and filling in some missing measurements. So in detail, the stereo matching algorithm works like this. So we extract the horizontal disparity of a certain contour point as observed from the left and right camera. So we have the contour here, and we have one from the left and from the right camera. And we look for the disparity, the difference between the two images in parallel for all the rows. And as there can be many other contour points in the single row, for example, 2 contour points for a single finger and 10 contour points for 5 fingers, we have to test for their compatibility to make sure that we are observing the same point on the silhouette from the 2 images. And so the compatibility is tested just based on the direction of the contour point and their location relative to the contour they sit in. And this is a combinatorial problem, and we solve it again with a dynamic programming approach, which gives us the best solution for all contour points along the row. So in the diagram right, we see the contour points ordered by their x direction in the x-axis, and the contour points from the right image in the y-axis. And with this cost matrix, we can simply trace the path with the lowest cost and find the best combination of matching the left and right contour images together. So the precision we get from FloodLight, FloodLight's depth estimation also enables a variety of features. For example, with a malleable reflective surface, we can detect hover, touch, as well as pressure information. So the blue column you see is the amount of pressure you put in. And we can also use FloodLight to detect and track pen or pen-like objects for like drawing applications. And this enables a precision quite similar to common graphics tablets. And the robust tracking also extends to physical objects in 3D space, allowing us to directly manipulate virtual objects that are mapped to physical tokens. So to get a better sense of the performance of FloodLight with real users, we conducted a comparative study with to evaluate the 3D pointing task with other state-of-the-art commercially available systems. So we compared FloodLight to Kinect with FloodLight's fingertip detection pipeline, which we call Kinect Lite, and to Leap Motion, and 3D gear system, which also utilizes the Kinect to detect certain hand poses. And we conducted the study with 12 participants, and we had 3,888 selections in total. And maybe not that surprisingly, FloodLight performed the best, requiring only 1.95 by 1.55 centimeters, approximately the width of the finger for the minimum target size, which is shown here on the left in black, closely followed by Kinect Lite, and then Leap Motion and 3-gear system, which requires a minimum target size of 5.3 by 3.15 centimeters. And we also compared their touch accuracy in a separate second study. And we asked participants participants to touch 12 grid points on a plane. And here we came up with a new physical setup where we enable touch sensing even for the Kinect and Leap motions, which were originally not intended for touch sensing. So we used a infrared absorbent paint, a sheet for the Leap motion, as you can see here on the bottom picture, and a transparent acrylic for the Kinect setup with laser-edged touch points. And this study also yielded similar results to the first study. Kinect FloodLight ranked first, followed by Kinect Lite, and then Leap motion and 3-gear systems. So FloodLight is a very flexible sensor platform, and there are so many ways to avenues we can follow in our research, in our future research. And as I said before, all the smarts in FloodLight are in the camera itself. So we could allow users to simply augment any existing physical device with touch and proximity awareness. And we can let users to simply cut and shape a virtually infinite number of input devices, like a 3D multi-touch mouse, a 3D trackpad, sensor strip, touchpads, buttons, and more. And in an experiment, we also found that common printer ink is transparent in the infrared spectrum, so they don't show up in the input images. So we can simply visually augment the reflectors with a custom user interface. So the computation part of FloodLight is fairly lightweight, which means that the whole system could be ported to a mobile device like a tablet and mobile phone. And with 3D input, user interaction wouldn't be any more limited to the physical size of the device itself. We can just use the whole 3D space around the user. And again, we did some initial experiments and found that the camera and the built-in LED flash in mobile devices already give us a very strong signal. So both videos were taken simultaneously, and here we can see on the right that the retroreflective material only appears as a strong signal on the camera with the LED flash turned on. And in the other camera, we don't even see the LED flash turned on. So the signal is strong enough for the sensor to pick up, but it wouldn't disturb or blind the user from like normally interacting in the same space. And we very recently we got hold of a phone with a stereo camera and LED flash very close to the lenses, and so we again did a quick experiment and found that in the two images the reflective material again sticks out fairly brightly. So we can just, for example, in a mobile use, we could have a smartphone which we carry around along with some other DIY widgets and like malleable sheets that you put in your pocket, and you could have access to 3D interaction anywhere. But potentially, we don't even require a stereo camera phones. We also investigated utilizing only a single mobile phone in FloodLight. We could use small mirrors and a red, green, blue splitting prism that is commonly used in the 3 LCD projectors and cameras. And we could just encode the left and right images of the scene into the two different color channels in an RGB image. And we wouldn't sacrifice on the field of view or the number of pixels to capture left and right images with a single sensor. Okay, so now I'd like to conclude this talk with a fairly simple sounding question. What is the future of desktop interaction? We don't know it yet, but we've tried to hook up FloodLight to Windows 8 anyway. So interactions work seamlessly with all multi-touch enabled apps. So this is Bing Maps in Internet Explorer, and we could just use normal multi-touch interactions on it for smooth navigation. But we can also use mid-air gestures for gaming scenarios, for example. And with a printed keyboard layout on top of the reflector, we can also type on it if we really want to, if we want to keep our hands on this interactive area. And then after finished typing, we can simply switch back to multi-touch mode and continue with our natural interactions. And finally, we let users reach for and grasp objects in a virtual environment that mimics the behavior of our own physical world. So will any of this really take off? I think we'll have to see and wait. And with that, I'll finish my talk and take your questions.
Any questions? Yep, at the back there.
Is it conceivable that the thing that is on the desk that you're interacting with could actually also be a screen so that you could project different things up, like that keyboard or some other stuff?
Yeah, so really interesting thing about the retroreflector is that it is highly angle dependent, so it's really good for the sensor. But for the output, it would be really bad. But there's one way to have a really good output, and that's by putting a pico projector next to the eye. So, for example, by having two pico projectors like next to your eyes, you could have stereo 3D output without like having anything in front of your eyes, just by putting the projectors on the either side of the eyes. So that could be used, but we can also use a normal LCD to use similar kind of interactions. I don't know if you've noticed, but you can use a polarizing filter like the one in 3D cinema glasses, and then point it at an LCD display, and then the LCD just turns black. You don't see any light coming from the display but the hand. And so we could use a large screen and use cameras with these polarizing filters on top, and then could have really clean segmentation of the hand itself. So we can. So the 3D contour sensing is not limited to the reflective materials, but there are so many ways to get a similar result with other ways of segmenting the foreground from the background.
Okay, any other questions? Very good. Thanks again. Really appreciate that.
Thank you.